Congratulations! Your hard work and perseverance have contributed to you being able to display a deep understanding of the current topics covered in class. You're a math master of this concept. I believe you're ready to learn the next things. You are among the few invited to participate in the learning of upper level concepts which go beyond what will be taught in class and in this grade level. It just builds upon what you've already been learning. Now, there's no obligation to do this, and you will not be penalized for not participating. Your only reward for its completion will be the extra credit in the gradebook and the value this excelled learning will have on your growing mind. Now, let's get started. Our topic is a closer look at triangles. Our essential question: what are some basic facts about triangles? Triangles are named more specifically based on their side lengths or angle measures. Right now, we're going to take a look at specific triangles whose names are based on their side lengths. We've got equilateral triangles, where all sides are the same length, and that's indicated by this tick mark right here. When they're all matching like that, that means that they are congruent. Another characteristic of equilateral triangles is that all of their angles are 60 degrees. Notice how the arcs on those labeled angles all match up. Again, those matching tick marks indicate that they are equal or congruent. Additionally, equilateral triangles have 3 lines of symmetry. That means you're able to fold on those lines of symmetry, and both of those sides on either side of the line of symmetry would match up. Another triangle that's named based on its side lengths is the isosceles triangle. Isosceles triangles have 2 equal side lengths, right there and right there, as indicated by those matching tick marks. 2 equal angles, check out those arcs with matching tick marks, and 1 line of symmetry. The line of symmetry on an isosceles triangle would be right there, where I would fold on that line, and both of those sides on either side of that line of symmetry would be congruent. Now, the third type of triangle named based on its side lengths is the scalene triangle. Scalene triangles have no equal side lengths. See how the tick marks on the scalene triangle are not matching? Additionally, there's no equal angles. And for scalene triangles, there's no lines of symmetry. My quick little question for you is, what do unmatching tick marks mean on a scalene triangle? What we're going to do next is we're going to take a look at specific triangle names based on their angle measures. Our first triangle is an acute triangle. With acute triangles, all the angles are acute, which means all the angles within an acute triangle are less than 90 degrees. And also, just so you know, it's possible to have an acute triangle that's also considered an isosceles triangle. And just so you know, it's possible to have an acute triangle that's also an isosceles triangle. It just depends on their overlapping characteristics. Now, the next triangle that we're going to talk about that's named specifically by its angle measures is the right triangle. Right triangles have one 90-degree angle, and the side that's directly across from that 90-degree angle is called the hypotenuse. And just so you know, it's possible to have a right isosceles triangle. It would be a triangle with a right angle and 2 equal sides. And the third type of triangle named based on its angle measures is an obtuse triangle. Obtuse triangles have one obtuse angle, which is an angle that's greater than 90 degrees. And just so you know, it's possible to have an obtuse isosceles triangle. That would be a triangle with an obtuse angle and 2 equal sides. Now that we've reviewed the various ways to name triangles, I want to go ahead and practice something that you should already know. So my reminder to you is that all the interior angles of a triangle will always have a sum of 180 degrees. So what I need you to do is you need to find the measurement of each missing angle within these triangles right here. I also want to tell you that these pictures, they're not drawn to scale. What that means is the measurements of the degrees that you do see right there, they're not accurate. So if you literally took a protractor and tried to measure that, it'd probably be a little bit off, okay? So take a second and solve for each unlabeled angle's degree measurements right now. So hopefully you pause the video. Here's the answers to the first 4 triangles. You'll see that when I take 90 degrees, add it to 30 degrees, we get 120 degrees. Well, 120 plus 60 gives us 180. So that's how I got the 60 degrees for this unknown angle measure. For this one right here, I knew that, well, 40 plus 40 is equal to 80. And I know that the sum of every single triangle's interior angles has to be 180. So the missing value when added to 80 needed to be 100 because 100 plus 80 is 180 degrees. And here are the answers to the unknown angle measures of the next 4 triangles. Right now, I want you to take a moment and respond to this question within your summary spot. What does not drawn to scale mean? All right, for our next set of practice, we're going to bump up the challenge just a tiny bit. You're math masters after all. So keep in mind that the sum of the interior angles of any triangle will always be 180 degrees. You want to also remember what you know about complementary and supplementary angles. Complementary angles are 2 angles that add up to equal 90 degrees. Supplementary angles are 2 angles that, when you add their degrees together, have a sum of 180 degrees. And let's not forget vertical angles. You might have seen me do this in class. Vertical angles would be right here, or here and here. And the special thing to remember about vertical angles is they're always going to be congruent. So take all that knowledge that you have right now, and I want you to find the measurement of each missing angle within these triangles. Again, these pictures are not drawn to scale. Pause the video right now so you can do this on your own. Now let's see how you did. To be completely honest, I might have gotten a little bit carried away with labeling all the degree measures for the ones that I saw that weren't labeled. So with these particular problems, you might have noticed that there's exterior angles. Exterior angles are angles that lie outside of the triangle. So in this example right here with number 9, this angle of A is an exterior angle. And for this particular example, it's 90 degrees. The way that I got that was, well, we know that every single triangle's interior sum of its degrees is 180. So when I took 55 plus 35, that was equal to 90. Well, I needed 90 more to make this inside angle's degrees have that sum of 180. Well, since this is 90 degrees and right here is a supplementary relationship, if this was 90, angle A also had to be 90 degrees. With this example right here, you'll notice that this is 68 degrees, this is 43 degrees, and that would mean that this angle right here would be 64 degrees, because 64 plus 68 plus 48 is 180. Well, if this angle is 64 degrees, then this angle measurement of angle Y is also 64 degrees because of what we know about vertical angles. Vertical angles are always congruent. From there, I noticed that right here, we've got a supplementary angle relationship. So if this is 64, angle X has to be 116 degrees because 64 plus 116 is equal to 180. And you'll notice that from here to here, we've got a vertical angle relationship. So if this is 116 degrees, so is this one. So I want to answer this little summary question. In problem number 13, what angle relationship is modeled by angle T and angle V? Right now we're going to expand on something we learned just a little bit in class. And we learned that when you add the lengths of the 2 shortest sides of a triangle, that sum will be greater than the third side. And if it's not, then a triangle can't be formed with those side lengths. Since my math masters go into more detail, that situation is actually called the triangle inequality theorem. We're going to go ahead and put that to use as we can determine whether these given lengths can join together to form a triangle. I'll do problem 14 with you. As the reminder shows us, we need to find the 2 shortest sides. In this particular example, that would be the side length that's 3 inches and the side length that's 4 inches. So I'm going to go ahead and write those down right now. Remember, this sum needs to be greater than the third side. So I know that I need to use this inequality symbol that implies that this is greater And it's got to be greater than that third side. So I'm going to put that 5 down right there. So when looking at this, 3 plus 4 is 7, and that needs to be greater than 5. And since 7 is greater than 5, we know that yes, a triangle can be formed using these side length measurements. Right now, pause the video and work through problems 15 through 18 and put that triangle inequality theorem to use. All right, after working through these, you should have found that the only other side lengths that can form a triangle can be found in problem number 17. The two smallest side lengths were 4 and 4, and when I take 4 and 4, that's greater than that third side length of 4. So therefore, a triangle can be formed. All right, so here's some brand new learning for you math masters. When you're given a right triangle, the side length that's directly across from that 90-degree angle is called the hypotenuse. And the other two side lengths are called legs. Something that you need to memorize as math masters is the Pythagorean theorem. And what the Pythagorean theorem does is it helps you identify the length of unknown side lengths of right triangles, as long as you're given 2 out of the 3 side lengths. The formula for the Pythagorean theorem that you need to memorize is the length of the leg, either one of them, squared, plus the length of the other leg, squared, is equal to the length of the hypotenuse, squared. Another way that you might see the formula for the Pythagorean theorem is like this. That first leg squared can be represented by the variable of a, and you got to square it. And the length of the other leg can be represented by the variable of b, but don't forget to square it when you put it in that formula. And the length of the hypotenuse, they represent with the variable of c, but don't forget to square it. Now, the reason that I prefer this first formula over this formula is because sometimes assessments try to trick you. And they might label a leg as the variable of c and the hypotenuse as the variable of a. When they mix it up like that, that really messes students up. So to be safe, when I teach it as leg squared plus the other leg squared is equal to the hypotenuse squared. But just know that this also represents a Pythagorean theorem. Be cautious to know that the hypotenuse squared will always be isolated no matter what variable is used. Before I have you practice applying the Pythagorean theorem, I want to show you the proof that the Pythagorean theorem does work and how it's derived. All right, not to make you hungry or anything, but if you have some Cheez-Its, go ahead and grab a box of them. What I want you to do is I want you to line up 3 Cheez-Its going this way and 4 Cheez-Its going this way. Then after that, stick 5 Cheez-Its that way, the diagonal. And you'll notice that this forms a right triangle. Well, this is going to be the proof that the Pythagorean theorem does work. We're going to label this side leg A and this side leg B. And of course, that side directly across from the 90-degree angle is the hypotenuse. And we're going to call it hypotenuse C. Next thing we'll do is we'll write down that formula for the Pythagorean theorem. A squared plus B squared is equal to C squared. And those lengths right there correspond to this triangle right over here. And we're going to insert the numbers in just a few moments. Let's go ahead and take a second and look at the definition of square. There's really 2 meanings. Just like the square, the shape with 4 equal straight sides and 4 right angles. And the other definition for square as it applies to math is it's the product of a number multiplied by itself. So let's go ahead and take a look at this example. If I had 5 to the second power or 5 squared, that really means 5 times 5. Well, here's a pictorial representation of that. You see how it's in the shape of a square, and I have 5 by 5. Well, if you counted each one of these squares right here, those little squares composing this big square, there's 25 of them. So you'll see that the number 25 is a perfect square. And when I take the square root of 25, that means how long is this side right there? It's 5. Okay, back to our Cheez-It problem. You'll see right here when I take this side length of 3 and I square it, I end up with 9 Cheez-Its right there. And when I take this side length of 4 and I square it, I end up with 16 Cheez-Its there. When we take this 5, that length of this hypotenuse, then we square it, we have 25 Cheez-Its there. So we're going to go ahead and insert those numbers into our Pythagorean theorem. You'll see we got that 3 from this length right there, and then when I squared it, it matches up with the Pythagorean theorem. And then when we take that B side length right there, which it was 4 units or 4 Cheez-Its, and we square it, it matches up in that Pythagorean theorem. And when you insert everything, we've also got that C, that hypotenuse of C. When I take that 5 and I square it, it looks like that within the Pythagorean theorem. So since 3 squared is 9 and 4 squared is 16 and 5 squared is 25, 16 plus 9 is equal to 25 and 25 is equal to 25. So therefore, this is proof that the Pythagorean theorem does work. All right, now that you've seen the Cheez-It example, let's go ahead and find the unknown side length for each right triangle. And these pictures are not drawn to scale. I'll help you with problem number 19. So you'll first need to identify that there is in fact a right triangle. And because there's a box right there, we know that this is a right triangle. So go ahead and write the formula for the Pythagorean theorem. I went ahead and I abbreviated it. Leg squared plus the other leg squared is equal to hypotenuse squared. The length of one of the legs is 3 centimeters, so I'm going to write that right underneath the formula, but don't forget to square it. And I've got to add to that the length of the other leg, which is 4 centimeters, and square that. The length of the hypotenuse is represented by the variable of x, so that's what I'm going to write over here, and I'm going to square that. Well, 3 to the second power, that's 9. And I've got to add to it 4 to the second power, which is 16. And I need to bring down my equal sign and my x squared, or x to the second power. From here, you'll see that I can simplify this side of the equal sign. 9 plus 16, that's 25. So now I've got 25 is equal to x squared. From here, I'm going to build it. So I started with x, and then I squared it. Well, the inverse operation of squaring something is taking the square root. So that's what I've got to do to both sides of this equal sign. When I take the square root of x squared, I'm left with x. And when I take the square root of 25, I'm left with 5. So the measurement of the hypotenuse of this right triangle is 5 centimeters. All right, Math Masters. Take your newfound knowledge of the Pythagorean theorem and solve for the lengths of the hypotenuse in problems 20 and 21. Pause the video so you can do that. All right, Math Masters, how'd you do? The side length for the hypotenuse in the triangle in problem number 20 is 2 5/10 feet. And the side length of the hypotenuse in the triangle in problem number 21 is 10 meters. For the summary, I want you to write this down. Another way to write the Pythagorean theorem is a squared plus b squared is equal to c squared. Label this a as the leg, label the b as the triangle's other leg, and label the c as the hypotenuse. All right, Math Masters, it's now time for your final challenge within this topic. You need to apply the Pythagorean theorem to solve for the unknown leg length of each one of these right triangles. Remember what you know about the Pythagorean theorem. To provide you some support, since this is probably some new material, I'm going to go ahead and help you with problem number 22. Watch closely. Start off by writing down the formula for the Pythagorean theorem. It's always good to have this as a guide, whether you're solving for an unknown hypotenuse or an unknown leg length when you're given a right triangle. You'll notice that one of the leg lengths right here is unknown, and they represent it with the variable of a. So underneath this right here, I'm going to write a to represent that side length, but I've got to remember to square it. I'm going to add to that the length of the other leg length, which is 40, and then I'm going to square that. And that sum is going to be equal to the length of the hypotenuse, which is 41. And I've got to square that. So now let's go ahead and simplify this problem a little bit. On this side of the equal sign, there's no like terms that I could combine. So I'm going to take a look at the other side. And there's nothing that I can combine, but you'll notice that I've got some values that need to be squared. So let's go ahead and do that on each side of the equal sign. 40 to the second power is 1,600, and 41 to the second power is 1,681. I got to remember to bring down my a squared. From here, I can build the equation in order to help me solve it. We started with a, and then we squared it. After that, we added 1,600. Well, the inverse operation of adding 1,600 is subtracting 1,600, so that's what we'll do to both sides of that equal sign. 1,600 minus 1,600 is 0, and 1,681 minus 1,600 leaves us with 81. So now we've got it simplified to a squared, or a to the second power, is equal to 81. Now I'm going to go ahead and move on up. Well, the inverse operation of squaring something is taking the square root. So I've got to do that to both sides of the equal sign. The square root of a squared is a, and the square root of 81 is 9. So the length of this unknown leg length is going to be 9 meters. Math masters, go ahead right now and pause this video so you can try problems 23 and 24 on your own. All right, how'd you do? For this leg length of this right triangle, I got 5 feet. And for this leg length of this right triangle, I got 12 centimeters. All right, for the summary, I want you to write down the formula for the Pythagorean theorem from memory.